Hello everyone, we're going to be starting chapter 8 now. So today we're going to talk about section 8.1, which is about the multiplication principle and permutations. So suppose your breakfast can consist of one pastry and one beverage. For the pastry, you have the choices of a bagel, a muffin, or a donut. And for your beverage, you have the options of coffee or juice. So we want to know how many different ways can we have our breakfast. So if there's 3 different pastry choices and 2 beverage choices, then essentially for every pastry choice you have 2 separate options for your beverage choice. So since we know that there's 3 pastry options, 2 beverage options for each, we essentially get 3 times 2. And we see here in figure 1 we have our tree diagram there. So we see that for every different item of breakfast we could have had, we had 2 separate options. So we see that we end up having 6 different ways of having our breakfast. So this is an example of the multiplication principle. So the multiplication principle, we want to suppose that n choices must be made with m sub 1 ways of making choice 1, m sub 2 ways of making choice 2, and so on with m sub n ways of making choice n. Then there are m sub 1 times m sub 2, and then we go all the way till we get to m sub n, which in this case, if we said, okay, there were 4 options, and we would have m sub 1 times m sub 2 times m sub 3 times m sub 4. So n is whatever value you want it to be, or whatever value is given in your problem. And this means that there are that many different ways to make an entire sequence of choices. So in essence, we're kind of thinking about a chain of choices. So for your first option, you have X amount of choices. For your second option, Y amount of choices. Third option, Z amount of choices. And so you want to just know how many different combinations of the choices can we end up having. All right, turning to an example, we have example 1, which is going to be your turn number 1 in the book. We have a combination lock can be set to open to any 4-digit sequence. How many sequences are possible, and what if no digits are repeated? So for part A, all we want to know is how many sequences are possible. In general, we don't care about repetition, things like that. So starting with A, and if we're thinking about a combination lock, we know that combination locks have 4-digit sequences with every digit slot has the option of choosing 0 through 9. So we know that on a combination lock, we have the numbers 0 through 9 that we can choose for every one of our digit slots inside of our 4-digit sequence. So this means that we have 10 digits to choose from. Here we'll go. So 10 digits to choose from. All right, so we have 4 slots, 10 digits to choose from for each slot. We don't care about repetition. So we're going to end up having is 10, which is M1 times 10, which is M2 times 10, which is M3 times 10, which is M4. So we see this 4-digit sequence. Each slot has 10 different options. We don't care about repetition, just any number. So we end up with 10 times 10 times 10 times 10. Now we see this is also going to be equal to 10 to the 4th power, and that's going to be equal to 10,000. So we get that there's 10,000 possible sequences. So that's what we would do if we just want to fill each slot with any digit between 0 and 9. Now for part B, we say, well, what if no digits are repeated? We still have all the same concepts as we did in part A. So we know it's a 4-digit sequence. Every digit slot has the option of 0 through 9, and we have 10 digits to choose from in each case. So we can say, still have 10 choices for our first slot. But if we want no repetition, and for an example, in our very first slot, we pick the number 3, and we don't want it to be repeated at all, that means that on our second slot, we now have 9 options because we're considering every number that's not 3. So then we say, now we have 9 options for the second. Then maybe let's say we picked 5 as our second slot. So now for our third slot, we don't want the number 3 and we don't want the number 5. So we want any number between 0 and 9 that's not 3 and it's not 5. So that means that we have 8 options. We say then 8 options for the third. And let's say you picked 9 as your third option. So now for your fourth option, you want any number that's not 3, 5, or 9. So which means that between the numbers of 0 and 9, 3 numbers can't be used. So we see, finally, we have 7 options for the fourth slot. So now, when we calculate this, we'll calculate it the same way since we know the multiplication principle. And we know that our first slot will have 10 choices, so that's going to be M1. Our second slot will have 9 choices, and that'll be M2. Our third slot will have 8 choices, that will be M3. And our fourth slot is going to have 7 choices, or M4. So without any repetition, we see that our numbers are going in descending order by 1. So we see we have 10, 9, 8, 7 for our first 4 slots, or for, in total, our 4 slots, because we only get 4. So when we multiply these values together, we end up getting 5,040 possible sequences. So we see that when we don't want repetition, we have to essentially take that value out of our entire range of values in order to correctly calculate how many combinations we would have in that case, or how many possible sequences in the context of our question. All right, moving on to example 2. We have Morse code uses a sequence of dots and dashes to represent letters and words. How many sequences are possible with at most 4 symbols? So if we think of the words at most 4 symbols, we mean 4 or less. So you can say at most 4, that's going to be equal to 1 or 2 or 3 or 4. Because we don't want anything larger than 4, but we can include 4 and then anything less than 4. So in this case, since we know that each symbol has to be a dash, so we say each symbol has to be a dot or a dash. We know that there's going to be 2 options. So we see 2 options. So now we can calculate how many numbers of possible sequences. And we have our little table here, and we know if we have a certain number of symbols, say we have 1, 2, 3, and it looks like I left off the last mark here, so I'll just continue that one. So we have 1, 2, 3, and 4. So thinking about this logically, if we have 1 symbol and there's 2 options for 1 symbol, dot or dash, then our number of sequences is going to just be 2, because this means we can either have a dot or a dash, since it's only one symbol. Then if we think about 2 symbols, we know that that means 2 dots, 2 dashes, dot dash, or dash dot. So it's going to end up being 4. But what we can say, since we know the multiplication principle, is that we know there's 2 options for our symbol and 2 numbers of symbols, and this is going to give us 4. Now, if we want to think about each symbol, dot or dash, for the number of 3 symbols, this is going to make it more difficult, because we see that for our original 2 options, we will have another 2 options for each, and then for each of those options, we'll have another 2. And since we know our multiplication principle, we know this is going to be 2 times 2 times 2. Because we have 3 numbers of symbols, so 3 separate occasions, and each time we have 2 options. So this would be like saying 2 is M1, 2 is M2, and 2 is M3. And we get this is going to be equal to 8. Yeah. Then for 4, we know, same thing as before. Now we're thinking about having 4 different occasions, so M1, M2, M3, M4. We have 2 options we know for each. So we're going to say 2 times 2 times 2 times 2. And that's going to give us 16. All right, so since we know each number of sequences that corresponds to each one of our numbers of symbols, we want to know how many sequences are possible with at most 4 symbols. So now we've calculated for 1, 2, 3, and 4. So our final step we want to add all of the possible sequences. For our first one, we know we had 2. For our second, we had 4. Third, we had 8. Fourth, we had 16. And when we add these up, we get that there is in all 30 possible sequences. So when I ask you a question like that, when it says at most 4 or at least something, we know that whatever numbers we end up deciding that that means, we add them all up at the end, and that would be our number of possible sequences. All right. Moving on to example 3 here, which is going to be your turn, number 2. A teacher is lining up 8 students for a spelling bee. How many different lineups are possible? So this means that 8 choices need to be made, or that we need to fill 8 slots. Because there's 8 students, we're aligning them all up, so that means that there's going to be 8 spots. So any student can be chosen for, we're going to change slots to spots. So any student can be chosen for the first spot. So this means there are 8 options for the first spot. So we can start lining these up. And let's pull this. Let's put it right here. Say there's 1, 2, 3, 4, 5, 6, 7, 8. So we'll say M1, M2, M3, M4, M5, M6, M7, M8. So we have our 8 spots. We know each one of these corresponds to a different spot. We know we have 8 choices. And we know that for our very first spot, we can choose from any one of our 8 students. So this means that we have 8 options. So we say for M1, we have 8. Then we'll choose that student and we'll put them there. So then for our second spot, let's say for the second spot, we now have 7 choices, since we chose that one student out of the 8. So now we have 7 left over. So for our second spot, we have 7 choices, so we can fill that in with 7. I'll just put in the multiplication signs. There you go. So then, if you could have guessed, for our third spot, 2 of our students would have already been picked, so now we have 6 options. So for third spot, we now have 6 options. So now after our third spot, we have chosen 3 students out of 8. Now we have 5 choices left over. So we kind of see where this is going. We already have an 8, 7, 6. So we can assume that this is going to go 5, 4, 3, 2, and 1. Since we have all 8 choices in our very first spot, 7 choices in our second because we chose 1 already, 6 choices in our third because we chose 2 already, 5 choices in our fourth because we already picked 3, 4 choices in our fifth because we already picked 4, 3 choices in our sixth spot because we already picked 5, 2 choices in our 7th spot because we already picked 6, and then we see just 1 choice lastly for our last spot since we already chose the previous 7. So we can just fill in our last one. So we can say for the last spot, we have 1 option. So now we have our multiplication here, or we use our multiplication principle to get this value, and we say we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we go from 8 all the way down to 1, and we just get to multiply these values together. So highly encourage you to multiply this on your own, and you should end up getting that there's 40,320 possible lineups. So that's how many possible lineups we have just by choosing 8 different students to put in a line. So there's a lot of different possible lineups we could have, even with just 8 students. All right. So the use of the multiplication principle often leads to patterns like the one we just saw where we had 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Or we know this, or we can call this the product of all the natural numbers from 8 to 1. So that just means that when we say the natural numbers, we know it's positive whole numbers, so 1, 2, 3, 4, 5 to infinity. So we know that by saying it's product of all the natural numbers from 8 to 1, we know that means 8, 7, 6, 5 down to 1. So we call this a factorial, this pattern of going from one number all the way down to 1 and multiplying by every whole number or every natural number in between. We call this a factorial. So if n is a natural number and we want the pattern that we just saw, so n times n minus 1 times n minus 2, and we go on and on until we hit 1, we would indicate this as n with an exclamation point, and we read that as n factorial. So in the problem that we just saw, since we went from 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we saw this exact pattern, so we would have called that 8 factorial. And by saying that, we just mean that we want to multiply by every whole number down until we get to 1. So this denotes the product of the values from n down to 1. That's how you get n factorial. Also, just a side note that we see, if n is equal to 1, then 1 factorial is just going to be equal to 1, because that's one option if you only have 1. So we see our official definition for a factorial notation. We have for any natural number n factorial is equal to n times n minus 1 times n minus 2, and we just keep going and going until we get down to the numbers that are 3 times 2 times 1. Also, by definition, we have here that 0 factorial is 1. And we kind of get this by the thought process of saying if there is 0 factorial, that's still one option because we're counting 0 as an option. So 0 factorial would be equal to 1. So we can also use this notation to show that n factorial is equal to n times n minus 1 factorial. And we know this because if we see our pattern that we had from our last equation with the 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we see that if we have 8 factorial, if we kind of sub that 8 out, we're going to end up with 8 times, and then in parentheses, 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's like saying 8 times 7 factorial. And we can kind of sub out these values as much as we need to until we kind of get what we want to get. So we can do this and just know that this is a property that we can use. We can kind of factor out that first or second or third. You can factor out as many as you want out of that factorial. But just know that that is the kind of like notation that we do to show that it's always n times n minus 1, or n times n minus 1 times n minus 2 factorial, or something along those lines. And this is only when n is greater than or equal to 2. You can't do this one. It's going to be 1, and then it just doesn't make sense. So when n is greater than or equal to 2, you can do this. Also, your calculator should be able to compute any factorial up to n less than or equal to 13. And if you want to go ahead and try this, this is because if you put in 13 factorial into your calculator, you're going to get an extremely large number. So we see that even a number that is not that big, like numbers like a 13, we see that when we have that factorial, it grows immensely large. So we can really compute any factorial that's going to be less than 13 into a calculator. All right, we have example 4 here, which is going to be your turn number 3. And also just a note, we're going to refer to this example very often, even in the next section. So just kind of keep this in mind. Just make sure that you're familiar with this problem. We have a teacher wishes to place 5 out of 8 books on her shelf. How many arrangement of 5 books are possible? So we have 8 books in total, and we have 5 slots on the bookshelf. So now we're kind of thinking about a different scenario where we have a different number of options for a smaller number of slots. So we use the same kind of theory here though. So we know that for the first slot, we have all 8 options. For the second, we have 1 less option because we chose one, so now we have 7 options. For the third slot, we now have 2 less options, so we have 6 options. For the fourth slot, we have 3 less options, so we have 5 options. And then lastly, for the fifth slot, we have 4 less options out of 8, which means that we have 4 options left. And we just stop here. We had 5 slots that we could have filled with 8 total books. We have our 5 slots, we have the number of options we have for filling each of these slots, and we just stop there. So now we can find this value. So we can say, so we get, and we want to fill in our slots. So let's say it's first slot, second slot, third slot, fourth slot, fifth slot. We can label this just as before. And we know how many options we have. In our first slot, we know we have all 8. In our second, we know we have 7. In our sixth, we know, sorry, in our third, we know we have 6. In our fourth, we know we have 5. And in our, oh, I wrote that twice, didn't I? In our fifth slot, we know we have 4 options. So we have now 8 times 7 times 6 times 5 times 4. So it's not a factorial because we don't go all the way down to 1. We just go to 4. So when we write this, we just write 8 times 7 times 6 times 5 times 4. That's it. So we multiply these values together, which I highly encourage that you do on your own. And you should get 6,720 possible arrangements. So this is our number of possible arrangements for having 8 books that we could have chosen for 5 slots. Now, like I said, we're going to refer to this example a lot, so kind of just keep it in the back of your memory. Now moving on to permutations. We have the answer from example 4. Example 4 is called the number of permutations of 8 things taken 5 at a time. So this is another just way that we can say it by saying if we had 5 slots and 8 options, we would say we have 8 things and we're going to take them 5 at a time. So a permutation of R, where R is greater than 1 elements of a set of n elements, is any specific ordering or arrangement without repetition. So the without repetition is very important. Without repetition of the R number of elements. The number of permutation of n things taken R at a time, with R being less than or equal to n, is written as P of n comma R. So based on example 4, since we know we had 8 options and 5 slots, in this case we're going to set 8 as n and we're going to set R as 5, since we see that we're going to take 5 elements out of the total 4. So when we write this, we know that P of 8 comma 5 is going to be equal to 8 times 7 times 6 times 5 times 4. This doesn't mean that we just go to 5. It means that we have 5 different slots or 5 different sections, or however you want to remember this as. We normally will call it events, since that's how we have called our sets before. So we could say 5 events. So this means 8 options or 8 elements, and then we're taking 5 elements at a time. So when we do this, we know it's going to be 8 times 7 times 6 times 5 times 4. So we see there's going to be 5 events, or in this case, we know m sub 5. We're going up to m sub 5. And we know that that's 6,720 options. Now we can use factorials to calculate this. So if we want to use our factorials, since we know our answer that we got before was 8 times 7 times 6 times 5 times 4, if we want to use factorials, what we can do is take this value, and we know that we can multiply any value by any value that's going to be equal to the value of 1. And we can take this 8 times 7 times 6 times 5 times 4, and let's multiply it by the value of 3 times 2 times 1 divided by 3 times 2 times 1. This means that when we multiply it all together, we're going to end up getting 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. We now see that we have a factorial in the numerator and in the denominator. And when we rewrite this, we rewrite it as 8 factorial divided by 3 factorial. So, and since we know it's 3 factorial, R was our number 5, N was 8, we can rewrite this and know that 8 factorial divided by 8 minus 5 factorial. And this gives us our formula of a permutation. So for permutations, if P of n comma r, where r is less than or equal to n, so r always has to be less than or equal to n because you can't take 10 options out of 3, you know. So it has to be less than your total number of elements or equal to, you can also have equal to, is the number of permutations of n elements taken r at a time, then P of n comma r is equal to n factorial, so your total amount of options factorial, divided by n minus r factorial. So that's your total minus your number of r. So your r elements taken at a time subtracted from your total elements, and that factorial as well. So a caution here. The letter P represents permutations, not probabilities. So don't think of this as the probability at n and r or something. It's the permutation of n taken r times. In probability notation, the quantity in parentheses describes an event. So in permutation notation, the quantity in parentheses always comprises 2 numbers. So if you see, you know, if you're thinking just in terms of notation here, if we see P of 1 value, that means probability. If we see P of 2 values, that means permutation. We always will see it like that. So if it has 2 values, it's permutation, 1 value, probability. All right. I included the proof of this just so we could kind of see how it works, but don't worry yourself with like memorizing this or anything. This is just kind of show you how we get this formula. So we have the proof of the permutations rule, and so we see that there are n ways to choose the first of r elements, n minus 1 ways to choose the second, n minus r plus 1 to choose the rth element. So when we end up getting the permutation of n and r is equal to n times n minus 1 times n minus 2, and then we go all the way down to n minus r plus 1. So now I multiply on the right by our n minus 1 factorial divided by n minus r factorial, which is what we saw before when we multiplied by the 3 times 2 times 1 divided by 3 times 2 times 1. We are multiplying by n minus r factorial. That was our 8 minus 5 factorial, which was 3 factorial. So we multiply by 3 factorial. So just like how we saw before, we end up with our values that are going from n down to n minus r plus 1. And then we multiply by the fraction of n minus r factorial divided by n minus r factorial. Then we saw when we multiply these all together, what essentially we end up getting is that we complete the factorial of our numerator, and now we have another factorial in our denominator. So it's fairly straightforward, and we kind of show it here as well if you just want to look at real values. That is how you would derive your equation. Also, since we defined 0 factorial equal to 1, the formula for permutations gives the special case, where if we have the permutation of n comma n, so this means that if r was equal to n, we end up getting n factorial divided by n minus n factorial, which is going to give us n factorial divided by 0 factorial, which we already said was 1. So this essentially is n factorial divided by 1, which is equal to n factorial. So if we ever get that value, we know what that is going to be. So we see that permutations follow the multiplication principle because P of n gives the number of permutations of n objects, therefore n choices for your first option, n minus 1 for the second, so on and so forth down to 1. So P of n, the number, or P of n comma n, the number of permutations of a set with n elements is n factorial. That is, the permutation of n and n is equal to n factorial. So really just the key fact to get from all of that was just that P of n comma n is essentially the multiplication principle. And so you're just going to get n factorial. That would be it. All right. Number 5, or example 5 here, which is also going to be your turn, number 4. We see that we find the number of permutations of the letters L, M, N, O, P, and Q if just 3 of the letters are used. So essentially what we're getting from this is that first, there you go. The number of permutations of the letters L, M, N, O, P, and Q can be found by P of n, comma n, which we know is n factorial. We see that L, M, N, O, P, and Q, that's 6 options, so 6 factorial. So we know that the total number of permutations is going to be 6 factorial. That's like if we wanted to use all of them in a sequence of 6 letters. That would be our total amount of permutations. But we're only using only using 3 letters, so we need P of 6, comma 3. So this is essentially our permutation of 6 elements taken 3 at a time. That's how we would say that. So using our definition, which we saw here, we have that P of 6, comma n, that's going to be 6 factorial divided by 6 minus 3 factorial. It's going to give us 6 factorial divided by 3 factorial. Oh, let's write that out. We'll have 6 minus 3 factorial. 6 factorial divided by 3. There we go. So that's what we're going to end up getting. And if you go ahead and plug this in your calculator, which you can do, your calculator can do permutations. If you're using an online calculator, you would just write your number and an exclamation point, and it pretty much gets what you're talking about. In your calculator, there's a different way to do it, which I will show you at some point in the lecture. But it's also in your book as well. In this section, it tells you how to calculate permutation using a typical calculator. So we end up with this value. And if you calculate this, you should end up getting 120 sequences or options. So we know we have 120 options of using just 3 letters out of L, M, N, O, P, and Q. All right. So now we know how to calculate a permutation, and we know how to, that we can just put it into a calculator. But now we can say to find the permutation of n, comma r, we can use our permutation definition and plug our equation into a calculator, like example 5, like how we just saw. We can just plug that straight into a calculator. Or we can extend our factorials to use the multiplication principle. This is what we're about to do in example 6. So you're going to see kind of how to do it by hand. So we see here in example 6, in a school election, 7 students ran for student body president. How many ways could students rank their first, second, and third choices? So if we're thinking about our first, second, and third choices here, we know that there's 7 options. We're going to be ranking 3 of them, or let's set our values so we can say that n is going to be equal to 7. We're taking 3, so r elements out of 7, and we say that r is going to be equal to 3. This means that we get the permutation of 7 comma 3, so 3 events out of 7 elements. So that means that we have 7 options in our first choice, 6 options in our second, 5 options in our third. And we see this is M1, M2, M3. So these are the values, and if we just multiply these values together, we end up getting 210. So we knew that was that. But in some cases with permutations, you're going to have much larger numbers, and you just don't want to calculate that. You don't want to do 7 times 6 times 5 and go down and down until a certain number of values. So that's why we use our permutation formula, because these are going to get much bigger, messier. So we want to know our formula. But we know that alternatively, we can extend our factorials to get, also going back to the one that we just had, we see that our options were 7 times 6 times 5. That was also equal to 7 factorial divided by 7 minus 3 factorial, or 7 factorial divided by 4 factorial. That's another way to write it. So, kind of starting with what we just had, we know this was 210. Starting with what we just had, we have our permutation of 7 elements taken 3 at a time. We know this is 7 factorial divided by 7 minus 3 factorial, which simplifies to 7 factorial divided by 4 factorial. So now what we want to do is extend our factorials. We want to take away our exclamation points, and we're going to have them go from 7 multiplied down to 1 for our numerator in this case. So we have 7 times 6 times 5 times 4 times 3 times 2 times 1. Now we want to extend our denominator, which is 4 factorial. So we're going to extend out our 4 factorial. This is going to give us 4 times 3 times 2 times 1. Now, in cases of fractions, when you have a certain number divided by another certain number, and you know you want to simplify that fraction, you can kind of think about what numbers that you can divide each term by, cancel them out, simplify. So essentially what we're doing here is we're just going to simplify this equation. We see here there is a 4 being multiplied in our numerator and a 4 being multiplied in our denominator. So we can cancel those out. We also see that there is a 3 being multiplied in our numerator and a 3 being multiplied in our denominator. So we can cancel those out. We see there's a 2 being multiplied in our numerator and a 2 being multiplied in our denominator. So we cancel that as well. And then there's a 1 in our numerator multiplied also by a 1 in our denominator. Those are just 1 anyway, but we're going to cancel those out. So what we end up left with is nothing in our denominator. And when we say nothing, we really mean it's 1 in our denominator. And then we have 7 times 6 times 5 in our numerator. This is going to give us 7 times 6 times 5. And we know that that value is equal to 210. So now we can say this is how we can calculate permutations by hand. So this is how we'd be doing it by hand. In cases where we have, 7 and 3, it's not too bad. We cancel out some numbers, we're left with 7 times 6 times 5. In other cases, it's going to be really long, so it may just be best to use your calculator. In other cases, it can be actually pretty short, so maybe by hand would be the best way. These are just different ways that you can use to find the same answer. And I wrote that twice. All right. So now here for figure 3, or our little blurb here, we have that graphing calculators have the capacity to compute permutations. So if you have a graphing calculator, you can definitely compute permutations. I'm unsure if scientific calculators can. Maybe you can, maybe you can't. Just look for the exclamation point, or something that looks like a little n, capital P, and a little R. But definitely in graphing calculators, you can plug this in. So we see, for example, like on something like a TI-84 plus or something. We have our P of 8 and 3 can be calculated by inputting 8 followed by NPR, which is found in your math probability menu, and a 3, which ends up yielding you 336 as shown in figure 3. So you would go to your math probability menu, you'd press that button, plug in your next value. It's pretty straightforward. There is a kind of longer blurb in the book about how to do this, and if you still can't figure it out, I'm sure there are like YouTube videos and stuff online. I'm sure I could personally figure it out on a calculator. I used to do it all the time, but that would also require me digging up my own graphing calculator, which I honestly don't know where it is. So anyway, we're going to continue on to our next word of caution here. We have, when calculating the number of permutations with the formula, do not try to cancel unlike factorials. For example, 8 factorial divided by 4 factorial is not equal to 2 factorial. 2 factorial is just 2 times 1 and it's equal to 2. But we see that when we actually extend out these values of 8 factorial and 4 factorial, that gives us 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. So we can cancel out our 4 times 3 times 2 times 1, but that leaves us with 8 times 7 times 6 times 5, which is equal to 1,680. 1,680 is very different than 2 factorial, which is equal to 2. So it's not straight division. When you receive factorial, you have to extend it all the way out, and then you can cancel the like terms. You cannot just divide by factorials. So keeping that in mind. Example 7 here, which is going to be your turn number 5. We have 2 freshmen, 2 sophomores, 2 juniors, and 3 seniors are all on a panel. In how many ways can the panelists be seated if each class must sit together? So what we see here is that we have 4 different groups. That's our freshmen, our sophomores, our juniors, and our seniors. So if we want to think about the ways that we can rearrange them, and they have to be by class, so they have to stay within their classes. They can move around within their classes, but they have to stay in their classes. This tells us, that there's 4 factorial ways of rearranging just by class. Okay. So there's 4 ways of rearranging just by our classes. But we also know that we can rearrange within our class based on the number of students that we have. So we can say, well, within classes, there are, and we see there's only 2 options for freshmen, so there's 2 different ways to rearrange them, which also means that there is 2 factorial ways to arrange freshmen. That's not a negative, I'm just making a point. I'll make that a dot. And then also for sophomores, there's 2 sophomores, so we have 2 factorial ways to arrange sophomores. There's also 2 juniors, so there's still going to be 2 factorial ways to arrange sophomores. And there's 3 seniors, which means there's 3 factorial ways to arrange seniors. 3 factorial ways to arrange seniors. So what we have is that there are 4 combinations or 4 factorial ways of rearranging by class, and then each one of our classes has a certain factorial and a way that they can arrange themselves. So what we do is we take our first value, which is always going to be our number or our ways of rearranging all of the classes in general. So this would be 4 factorial. And we can kind of put this in parentheses. And now we want to say, now we want there to be our factorials on how to rearrange each class. And since we know that there's only 4 classes, we'll say this is freshmen, sophomores, juniors, seniors. And we know there's 2 factorial ways to arrange freshmen, so 2 factorial. 2 factorial ways to arrange sophomores, 2 factorial ways to arrange juniors, and 3 factorial ways to arrange our seniors. So we see that we have every option and the way that they can arrange themselves, but then we have our 4 factorial, which is the ways that they can rearrange by class. All right, and then when we calculate this value, we end up getting 1,152 ways they can be seated. So in this case, we're really following our multiplication principle more than our permutations, because this is telling us that we have our number of options and then our numbers of options we can arrange within those options. So in this case, we're kind of thinking about the layering of it. So it's like we have our classes and then we have the people within our classes. So it's definitely a multi-layered problem. All right. So now we can do our last example, which is example 8. This is going to be number 33 in your book. And we have that a local television station has 11 slots for commercials during a special broadcast. 6 restaurants and 5 stores have bought slots for the broadcast. So for question A, we want to say in how many ways can the commercials be arranged? B is how many ways that can the commercials be arranged so that the restaurants are grouped together and the stores are grouped together. And then for part C, we have in how many ways can the commercials be arranged so that the restaurant and store commercials are alternating. So first, let's just start with problem A. So we know that there are 11 slots for commercials. If for part A, we just want to think about how many ways the commercials can be arranged, that means any order and no, we have no repetition because you can't repeat the commercial twice. There's 11 slots and we have 6 restaurants and 5 stores. So this can just be any real combination of the 6 restaurant commercials and the 5 store commercials that create 11 different commercial slots. So by logically thinking about this, we know there's 11 slots. They can be in any order, but we know without repetition. So this gives us 11 factorial. Since we don't care about repetition, we're just taking the total number of commercials and we're seeing how many different ways can we rearrange them. 11 factorial is going to give us 39,916,800 ways. So that is going to be our total number of ways that we can rearrange our commercials. Now let's move on to part B. So part B is, in how many ways can the commercials be arranged so that the restaurants are grouped together and the stores are grouped together? So this is kind of like the last problem that we did. This is going to be a multi-layered problem. So we see we have restaurant commercials and store commercials. That's two different categories. So we're going to have 2 factorial different ways of just rearranging our stores or restaurants. We can think about it, and this makes sense because there's really only 2 ways to do it if there's 2 categories. We either show the store commercials first and then the restaurant commercials, or we do the restaurant commercials first and the store commercials. So there's only 2 ways. But let's write this out. So if we want them grouped, we see it's just 2 categories. So 2 factorial. Then we know 5 choices for store commercials, 6 choices for restaurant commercials. I left a little spot here because we're going to say what this is going to coordinate to within our factorial. So if there's 5 options, we know that there's 5 factorial ways to rearrange our store commercials. So this is going to tell us 5 factorial. Same thing goes for 6. There's 6 choices for restaurant commercials, so we can rearrange our restaurant commercials in any order we want. And this is going to be 6 factorial. So just like in our last problem, we want to take our number of ways that we can rearrange the categories, then multiply by the number of choices we have in each category. When we multiply these values together, we're going to end up with 172,800 ways. So we see we definitely have significantly less ways that we can rearrange our commercials if we're thinking about grouping them by category. Then for part C, we say, in how many ways can the commercials be arranged so that the restaurant and store commercials are alternating? If we're thinking about alternating, we don't want any repetition. So we don't want to have a store commercial and then a store commercial, or a restaurant commercial and then a restaurant commercial. So the way that we can arrange these so that they're alternating and we have no repetitions is that we're going to start with our restaurant commercials. So we say we need to start with our restaurant commercials. So they are alternating without repetition. All right, so then we get, and let's make our 11 slots here. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have our 11 slots. And on a question like this is kind of when we want to write this out by hand. So we're going to start with a restaurant commercial. So we're going to call this R1. So our first restaurant commercial. There's going to be 6 restaurant commercials, so we have 6 options for our first slot. They need to be alternating, so now we're going to have our first store commercial. There's 5 store commercials, so we have 5 options. Now let's move on to our second restaurant slot. We've already chose 1 out of our 6, so now we have 5 options. And now for our second store slot, there were 5 options. We chose 1 already, so we have 4 options. For our third restaurant slot, we already chose 2 out of 6, so we have 4 options. For our third store slot, we already chose 2 out of our 5, so we have 3 options. For our fourth restaurant slot, we already chose 3 of our 6, so we have 3 options left. For our fourth store slot, we already chose 3 out of our 5, so we have 2 store options. For our fifth restaurant, we already chose 4 out of 6 of our commercials, so we have 2 left over. Then for our last store slot, since we had 5 store commercials, we already chose 4 of them. We have 1 option left. And for our last restaurant slot, we also have 1 option left. So that is how you would write that out if you wanted to think about alternating items. And in a case like this, you really want to write it out so you get a nice visual of kind of like what's going on. Now, when you multiply all these values together, you end up getting 86,400 ways to air alternating commercials. All right, and that was our last example here for our section 8.1, all about permutations and this multiplication principle that we kind of introduced. So we see it's just going to be really a lot of patterns, and then also knowing what values we're going to use in permutations, things along those lines. So like I said before, that example 4 is going to come up in next section as well. So if you could either keep that in mind or maybe copy it down somewhere, that will be very helpful for our next section that we're going to have a lecture on. All right, so as always, if you have any questions or concerns, please don't hesitate to email me, submit an anonymous question to the question form, or you can feel free to pop into my office hours at any time. All right, I will see you guys virtually later.